Balwinder Kaur, and he's my coworker, Joe Rickson. Both of us work at Aptina Imaging. So we've divided our talk today. We will cover right from the camera APIs to the Android framework and the camera service, going down to the CameraHAL, device drivers, and even hardware. And the top layers I will be covering, and midway through we will switch all these wires, and Joe will take over to talk about the CameraHAL, device drivers, and the hardware. So basically there are 6 classes and 8 callback interfaces. The classes, the main class of course is camera, and then the next most interesting and most complicated is camera parameters. We have camera info, camera size, camera face, and camera area. Info is really very simple. It just tells you whether your camera is a front-facing or rear-facing camera. It also tells you the orientation of the image that you're going to get back from that camera. Size, like the name says, is quite simple. It's just height and width of the image coming back. Area is a little complex, more because of the way it gets used rather than the API itself. It basically defines a rectangular area, and it has a weight. And you have to be more of a professional camera person to understand the metering regions and auto white balance and things like that. Camera.face is very interesting personally to me because it is the class in Ice Cream Sandwich. Android introduced face detection APIs, and this is the class that helps with giving back face data. And so most of the camera APIs are you take a picture and take a good picture, and how do you do? So basically it's a camera application is one of the use cases, but the more interesting ones. Yeah, it's behaving differently, yeah. The camera face it's what other things you can do. And with that, we'll get into more of the computer vision kind of applications. Face detection, and things like that. Personally, I find that very interesting, and I think there's going to be a huge slew of applications around that. Then we have callback interfaces, face detection, error callback. We'll talk about the picture preview and shutter callbacks when we go over the API for how to take a picture. The one that is in orange on the screen is the one new API that was introduced with Jellybean. It's the autofocus move callback, and I'll talk about that in a little bit. Camera class. So basically think of it as all the actions you would actually do with a physical camera. You have to open the camera. You have to shut it down at some point. You should be able to access all the controls, what is the scene mode, all those different controls. And I'll talk about that in the camera.parameters class. So what is one of the first things one does with the camera is preview. Basically, you see in your little viewfinder what is the scene that you're trying to take a picture of. And preview is pretty complicated. So I really never worked with cameras and all this before I joined Aptina, and to me it used to be a tiny little thing at the back of a cell phone. But after a year working there, I am just amazed at how much goes into that tiny little thing. So preview, it's such a big deal. Once they bring new hardware up, it's like if you get preview working, it's a major achievement. So now I've started treating preview with a lot of respect, more than I did a year back. How do you get live previews? In the callback. And then there are other things that I find quite interesting is how can you suppose you don't want to display anything. Let's say you're writing an app where you're using the camera for gesture recognition. All you want to see is the gesture. You don't really want to show that on your preview. So can you actually grab the preview frame but not display it? So we'll talk about that a little bit. Then, of course, it's capture. At the end of the day, for most applications, you do want to take that picture of your pet, your dog, your wife, whoever. Want to unlock and lock the camera. That's when we hand over access to the camera hardware to another process. And that is basically when you go from still mode to video mode, and then the media recorder comes into play. I'll show a little bit of the code for that as well. There are 3 basic actions that the camera class provides. Start autofocus. So before you actually take a picture, you want to kick up the autofocus to make sure that your object, the picture of what you're taking, is focused. Smooth zoom is used where you can smoothly zoom in and out of the picture. And the one that was introduced with ice cream sandwich is start face detection. OK, camera.parameter. So if you open up the developer page and the Java doc for this class, it runs into miles. But if you look at it, there are 3 patterns, and that's what I've broken up here, of the way the methods are named. There are some that are mandatory feature sets that any Android phone or device, I would say certified, right? I mean, you could really do nothing if you want to, but is expected to provide. Those start with the get supported, and then there will be something behind it. It could be preview sizes, picture formats, picture sizes, all kinds of things. So you can get a list of what scenes, modes, auto white balance. You can get a list of what is it that this particular device supports. And then you can do your gets and sets on it. The second is a list of optional feature set, because even Google recognizes that the hardware, the capabilities of the hardware is going to differ from device to device. And so there's the optional feature set. So some things like, is video stabilization supported? Right? Now that's a feature of the hardware, and all platforms don't have to support it. So for them, the pattern of the method is video stabilization supported? Is video snapshot supported? And then it has its corresponding get and set. The third is custom feature sets. So we have certain features, like Aptina is a hardware manufacturer. So we have certain features which are not part of the regular ones. And for that, we use, we call the custom feature sets or extensions. And we use the dump pipe that the architecture provides. It's just name value pairs with strings. And you can use the gets and sets for that. And then at the bottom, I have a whole list of what are the different things, list of methods that and features that a camera can provide. I briefly covered most of this. The camera face is coordinates for the left eye, right eye, mouth, outer bounds of the face, is what is covered by camera.face right now. However, you will find that a lot of the newer hardware can support a much bigger set of coordinates related to face data. OK, so what's new in Jellybean? When Ice Cream Sandwich came out, it came out with a huge set of APIs for camera. But Jellybean, there was one camera API, which is the autofocus move callback. Basically, there are different kinds of focus modes that you can put your camera into. If it is a continuous focus mode, either for still or video, the application at times needs to know whether the focus has started or it has stopped. And so this is what that callback provides. The other thing they provided was in the media package, and it's a set of sounds that if your application wants to use to mimic the shutter or the take picture callback that the system provides, you would use this. It's just convenience functions to use in your application. The most interesting part for Jellybean was that there is a new system camera application. So now if you look at the Jellybean source code under packages apps, it has the legacy camera and it has the new camera app. And the major difference is the support for gestures, which even the iOS 5 are talking about, is how you can, once you take a picture, normally you had to click on the thumbnail and bring up the gallery application to see what picture you take. But they've now provided support for gestures. So you can just flick right and see what the latest picture you took or others. And then the other gesture they have support for is the flick up to delete and undelete. But I think the bigger thing is I haven't had a chance to dig very deep into what the differences are. But the other thing is it's more this whole Jellybean buttery feel. So it's more about providing a smoother interface for the camera application. So one of the biggest things when developing a camera application is the time it takes to start up the camera, the time it takes to display the preview, and it could become a very jerky app. So a lot of optimizations are around how to create a smooth user interface, because what we're moving back and forth is a lot of data and a lot of time-consuming tasks. This is just a table that I had put together when we evaluated the ice cream sandwich features. And at that time, a lot of people got very confused, even internally, as to what was an API and what is part of the system app. And people were searching about, why can't I do face recognition? So we put a little table together to see what is part of the APIs, what's just in the system app, and what is actually closed-sourced and proprietary solution. So this table just reflects to that. So some of the prominent use cases when dealing with with the camera APIs is, of course, is the first to get your preview right. Second is to take a picture. Third is to save your picture. And then the fourth is to smoothly move from the still mode of a camera to a video mode. Some of the secondary use cases is to configure your camera the way you want it. You want a certain auto white balance, a scene mode, things like that. So this is more for what I would call a power user of the camera rather than a general user who just click and shoot. You would use that. Then we talked about it is how do you process the metadata, the face data. It could be frame data, histogram, all the metadata around an image. We have video snapshot, which was also introduced in ice cream sandwich as an API, but it's the hardware that actually needs to be able to support it. And in that case, what happens is you need to you have the camera in video recording mode. You should also be able to just maybe touch the screen or click a button and be able to get a full high resolution JPEG image. So one of the things is, as an application developer, if all you really want to do is you just want to take a picture or take a recording, you can use system intents for that. You don't really need the camera APIs for that. The camera APIs are if you really want to develop your own custom experience with getting a picture or taking a picture and things like that. So I would highly recommend that on the Android page, there's the link on the slide, which is a very good tutorial on how to do different things that you would want to do with the camera. So do check it out, and a lot of your at least beginner level questions will definitely get answered from there. Okay, at this point, I'm going to bring up Eclipse. So it's a simple activity, and I'll just describe the layout to you, or maybe we can take a look at this. So it's just in landscape mode. There's a shutter button on top. There's a little button where we switch between the two modes, and this will display the thumbnail once we have something to show. So very simple, basic app, camera app. Okay, so this is just some of our fields, and we can go straight to the onCreate. I'm sure you're pretty familiar with the inflating items and getting handles to them. So the first one is the shutter button, where once it gets clicked on, the first thing you do is call the autofocus. The next one is just a share button, so that which right now is invisible, so you couldn't see it. But all this does is that it gives you the capability to share with any of the apps that can filter the send intent. switch button, this one will toggle between the two modes, and I'll go over the code for that in a minute. So let's go and see how the preview works. So we need the custom surface callback, which so in this case, this implements a surface holder callback, which has three methods to implement: the surface destroyed, created, and changed. And once we have a surface is when we will actually open the camera and set the preview display to the holder. So there are two methods for preview. One is set preview display, and the other is set preview texture. And I will talk about that a little later on. This one helps the live preview stream is not returned back to the application. The preview frames go straight to the display. Now there are two other methods with preview if you want a copy of the frame back in the application. Yes, please? Do you have a question there, back there? Okay. One is the one-shot preview callback, and another is a callback where every single frame that gets sent to the display subsystem, a copy of that is made from the native memory into the memory space of the application and is returned back to the app. In the one-shot preview callback, only one time, whenever that call is set, the next preview frame, a copy of that is sent to the application. So under normal circumstances, if you don't want to do anything with the preview frame, you don't need to set the preview callback. It's only if you're trying to do something extra. And I'll talk about an open source project, which is a barcode reader, where they use the one-shot preview callback to get a copy of the preview frame, and then they process it to recognize what kind of barcode it is. So this one goes straight to the display. The set preview texture, on the other hand, is able to send the previews. It bypasses the display altogether, and you can send it either to the GPU or to the CPU. And I'll talk about that in a later slide. So once you have set the surface here, you can go ahead and start preview. Once you're in preview, this one is just a Boolean to say that, OK, we're now in preview mode. Now, the other interesting thing, the next use case is the ability to take a picture. So if we go back to our shutter, here, we started an autofocus with a autofocus callback. Once the callback returns, meaning that the image is now focused, it's when we will fire off the take picture call. Surface changed. Right. So we have take picture. There are two take picture calls that are available in the APIs. One of them takes 3 parameters, the other one takes 4. The first one in both cases, the shutter callback. So as soon as the shutter is clicked, you'll get a callback. So if you want to do anything with it, I don't know, maybe display stars or a sound. Normally people just do a sound. So if you want to do a custom sound or something, you would put that in the shutter callback. The next one is the raw callback. So if you are looking to get back raw data, and now, but the hardware has to support the capability to provide unencoded data back. And if you want to know what more is raw, you'll have to ask that question to Joe. He's our expert on different formats. The third one in this case is the JPEG callback. So far, I've never really seen the raw callback being used anywhere, or hardware that supports it, but it could be my limited knowledge. JPEG callback, of course, returns the JPEG image, so the picture which was taken. So the preview is typically at a lower resolution. It could be a VGA or something. And then the JPEG, you'll get a full resolution image. So if you have a 3 meg camera, it'll be probably 3 meg, 5 meg, 8 meg, whatever your camera supports. You can, of course, use the camera parameters to explicitly set the sizes of what kind of a size you want it. But by default, it's typically the highest resolution that the hardware supports. So once you do take picture, at this point, you get a callback which has the data and on picture taken. And so you have to restart preview. So yes, please.
I just want to ask about the post view.
OK, so the post view is some of the cameras hardware have a post view mode. And I wouldn't know the industry definition of post view, but I can tell you what the Aptina sensors do for post view. It's a high power mode, and there, instead of the preview being at a lower resolution, we have things that go at a full resolution. Is constantly streamed at full resolution. So at 8 megapixel sensor is constantly capturing in a circular buffer. It will capture images at 8 meg, and then we have a smaller resolution that gets piped as the preview. And when we come to the hardware section, Joe will go over the circular buffers and show you how it works.
So in this case, the post would be the 8 meg version?
Yes, it depends. It depends on the hardware, what they return in the post view callback.
Your interpretation of that would be?
So this is one of the things I have as missing things in the Android APIs, is what exactly does the post view mode mean? And we typically find that the supported sizes for preview and picture taken in post view don't always match the ones in regular.
There's no way to set the post view size.
Right, so we don't have that. So that API is also missing, right? And the way we worked around it internally is by using this camera.parameters and having specific modes. So we work around that. We actually explicitly set it into post view, and then we have strings that return all the supported size. So that's how we worked around it. But I think there is the need for this camera API, which talks about the post view mode and the functionality there. I mean, what are the capabilities in post view mode?
The API says fully scaled, but it does not say scale to what size.
No, it doesn't.
You think it would be the size of your display. That kind of would make sense.
Yes, it's not defined at all. And I believe it's not standardized, it's not defined, it's hardware dependent, so it's subject to interpretation. I think it's probably mostly used by OEMs because they know what their system capabilities is, versus a third-party developer actually being able to use the post-view callback reliably. So that's my take on it. Okay, so save picture is just an async task, and we'll just save it to the file system. And that's pretty much it. So with this, I'll just talk about how do we go from a still mode to the video mode. Switch video on right there. What's up? So one of the first things you have to do is you have to unlock the camera. So that right now the application has a handle to the camera, but when we get into video recording, we need the media recorder process to also be able to access the camera. And so the first thing you need to do is unlock. Create a new media recorder. These are just callbacks for errors and infos. You set the camera. You have to tell the camera, OK, this is the camera instance that I was using. You hand it over to the media recorder. You set your profile, set your video source, and set output file. What's the file name, duration, max file size. And then you also have to, again, provide the set preview display holder for that, the one that you had already created. And you start. No, I think you put prepare and then start. And the media recorder state diagram, for those of you who are familiar with the API, is pretty well documented. And if you miss even one of the calls somewhere in there, it will fail, and you will go into one of those catches there. Face detection. So face detection, you have to the way to detect, there's no is face detection a method to see whether face detection is supported or not. Instead, this one is get max number detect faces greater than 0. I'm not sure why the is face detected supported call is not there, but that's how it is. And if it is, then you can start face detection. So the way the API works is, and the way some of the camera stacks work is that then you will get a call, but you'll have a listener for the face detection listener, and then you have to do a lot of complicated math to figure out what the coordinates are and accordingly put overlays on your preview screen. Some of the newer ISPs will actually just put it on for you, but so we typically, I really haven't worked that much with the on-face detection callback because we just get ours overlaid on top. Okay, other applications. So this was where it's a non-camera application. So one of the things is I already talked about is it's an open source library for 1D, 2D pictures, and they use the one-shot preview callback, which I mentioned briefly. And I'll show you that application also, app demo at the end of the talk. Live preview without a display. And so this only started as recently as Honeycomb and basically went mainstream with Ice Cream Sandwich. So there is now support for GPU processing and CPU processing. So you can, and the way that works is, which I mentioned earlier too, is the set preview texture. So for you to work with GPU processing, you do need to know OpenGL, and you need to provide a context. And then there the call is surface texture.update text image. Whenever you make that call, the texture will actually get updated with the latest preview frame that is available. If you want to do, if you don't want to work with OpenGL code, you can still have a surface texture, but use just a dummy ID instead. In this case, it gets piped to the CPU, not the GPU, and it's not as efficient, of course, as sending things to the GPU, but then you don't need to know OpenGL. And what I saw was that the OpenCV sample codes, for those of you who are maybe new to this, OpenCV is the open source computer vision library. In all of their sample code for Android, they use this option number 2. And I have a few demos that I can show at the end, apps, they're just sample apps straight from OpenCV that show. But the real interesting ones, use cases for this, is the Google I/O 2011 talk. And there's a link here. I'm sure the slides will be available, right? There must be a way to make them available. Okay, so that is really interesting, and they have a lot of use cases of how actually you would use the preview and do a lot of fun things. So I would recommend that you take a look at that afterwards. Android Media Framework. Okay, so most of you have seen this four-colored, Google-colored diagram, and that is the CameraHAL, the piece that we work on mostly. Okay, so it's basically, if you're familiar with the architecture, there's the hardware-independent piece and the hardware-dependent piece. The hardware-independent piece is the application framework, which is mostly written in Java, and then we have the camera service, which is native code, and everything below that yellow line is all hardware dependent, and the hardware, the OEMs or the hardware manufacturers typically are the ones who implement those pieces. So how does it work? We have an application, and so the camera service lives within the media server process, and once an application makes a request for the mCamera.open call, it will make a call to camera service over the binder interface, and a camera object is requested from the hardware. It also creates a connection to the surface flinger so that the preview frames can be displayed. If there's another application and it makes a request to the front-facing camera, that one will also get serviced. But if there is already an application has a handle open to one of the cameras, then the other applications get refused. So as a good Android citizen, if you're an app developer, in your on resume and on pause, you need to release and connect your camera. Otherwise, other applications will not be able to use it. So inside the camera app, that's what it looks like. There's a JNI layer. The camera service, which is hardware independent, resides in the libcameraservice.so shared library. So what does the code in the JNI layer, the Android hardware camera, do? It basically creates a persistent context for all the callbacks that come from the native layer. It holds references to the Java camera object, face object, and area object. So one thing to remember is that a copy of the JPEG or the preview frame is made here in this layer. So it is expensive. If you're thinking of doing the preview callbacks, just remember that your actually copies of frames are happening. So it is expensive. It's basically a resource manager for the camera hardware. This is the one that checks for permission. So you do have to declare your hardware permissions in your application for you to be able to use this one. It keeps information about how many cameras are available, their orientation, and things like this. So this is the open source folder structure, and it's probably too small to see, but where different pieces of the code live. And interestingly, this got changed in Jellybean, and things moved from frameworks base to frameworks AV. But when I looked at did a diff of all the folders, I didn't find too much of a difference in the code. It's more like bug fixes or support for the new API called the autofocus move callback. So I didn't see any major difference in the code base. They just moved it around. And with that, it's going to be all about Joe. So.
Hi, my name is Joe Rickson, and I'm a software engineer for Aptina. Similar to Balwinder, I work in the driver group. We do device drivers and also low-level software. And so the next section we're going to talk about is the hardware dependence section. We'll start out with the CameraHAL. And I'll be talking about the three areas here, CameraHAL, followed by a kernel device driver, and then a little bit on sensor hardware. So the the CameraHAL is a library that's specific to the hardware, and this is usually written by the hardware vendors, TI, Qualcomm, or others. CameraHAL interfaces with the camera services stack that's right above it, and it does so through, for Froyo it used a camera hardware interface, and for Ice Cream Sandwich it uses camera.h. And CameraHAL interfaces with the lower level driver. In this case, I'm talking about video for Linux, but there is also other interfaces that it could talk to. It could be OpenMax or even others. And when it's talking with video for Linux, it uses file I/O operations. This gives a block diagram of the CameraHAL, and this is based on TI's OMAP4 open source code that we use. And so in this block diagram, CameraHAL block is sort of the quarterback for all the other blocks. Memory manager, display surface manager, event notification, and the lowest level one is camera manager. Each of the blocks are specific to the hardware that's running, and so depending on the hardware platform, Qualcomm might have it a little bit different than TI. Some of the functions of the CameraHAL block are initialization. So this will initialize everything from the CameraHAL on down. It'll initialize a device driver, and it'll also initialize the hardware and get it ready for previewing or whatever. Camera services interface, everything that's sent from the top layers is handled by this block also, dispatching it either internally or to the drivers. And then the camera state machine is also maintained here too. And this is, the camera is a state machine. It moves from standby to preview, from preview to capture, from preview to video. It doesn't just sort of jump around into different things. You don't move from standby into capture, for example. And so a state machine has to be maintained by the CameraHAL. Memory manager cameras, as you probably are aware, are very memory intensive. So you want to have a good memory manager to allocate buffers properly and free them when they're not in use any longer. The display surface manager controls preview activity between CameraHAL and the display device. And so it coordinates back and forth of the display process. It sends frames to the display when they're ready for preview, and then also signals to the lower level driver when buffers can be queued or unqueued. Event notification, there's several events that get called back up into application space that I'm sure you're aware of. Those are broken down into 3 broad events at this level. There's notify, which you get called on when there's an error or a zoom event or a shutter event or things of that sort. There's a timestamp, which is used for video frame stamping, and then data callback when preview, if there's a preview callback, compressed images or post-view images. And the lowest level is the one called Camera Manager or Camera Adapter, and this talks directly to the underlying device driver or rendering software. For a use case for this, what I did is I chose preview. So we'll take a look at what CameraHAL does for preview, then what the driver does for preview, and then underneath it what happens in hardware when preview is executed. Preview is displaying the camera image in real time, as I'm sure you're aware. And so the camera passes that image straight over to the display device. From the application view, that's a single call, but from everything down below that, that's many calls and many different things. This sequence diagram here gives an overview of all the different calls that sort of go on. So a single call from the application down to camera server. Then from CameraHAL down, there was a number of different calls, what we call ioctals, in between the CameraHAL and the device driver. So the first one would be to set the format of the camera image. It would be set the resolution, which is the size, and then the image format, maybe YUV or RGB or whatever. The next one is requesting buffers. The Video for Linux organizes camera screenshots in buffers. It will take a whole slew of buffers and do that in a circular list. And this is important for keeping the camera moving and not dropping frames and things like that. So requesting the buffers is an important part. If buffers are allocated in kernel space versus user space, we want to query the buffers, find out things about them, and then map them into the memory space for user space. Last 2 things, we queue up the buffers into our internal queue, and then stream on turns on preview, and that starts the camera pipeline flowing. The next slide here shows what happens during preview operation. The hardware receives a preview image. It signals to the driver that a preview is ready. The driver in turn signals to CameraHAL that a preview image is ready. CameraHAL will take that image or a pointer to that image, dequeue it out of the queue of buffers, and then pass that off to the display device, which will either copy it into the display memory or pass it off as a memory mapped object into display. And if a preview callback is enabled, then that'll be copied for user space. Next section, we're going to go down one more level, and we'll talk about the camera driver at kernel level. Previously for a CameraHAL, everything above that is in terms of streams and parameters and things of this nature, things that you're familiar with from the application level. At this level down below, everything is in terms of register writes, data being transferred over parallel and MIPI lines, things of that sort. So the kernel driver represents a standard interface for different types of camera hardware. So what this means is that you may have various different types of camera hardware below this, but at that level of the Video for Linux or OpenMax or whatever, it's a standardized level, and that's what CameraHAL will connect into. It can support different types of hardware topologies, such as an image sensor processor, which I'll talk about in a little bit, versus a smart sensor are handled at this level. And Video for Linux does a pretty good job of handling these things. This block diagram just gives an overview of a typical Video for Linux driver. The top layer contains all the file I/O calls that are used between CameraHAL and the driver. Also, the driver infrastructure is routed here. The controlling interface controls data flow and control flow. On the lower right-hand side, each camera will have its own file that'll have all its hardware-dependent parts in it, how to detect the camera, how to initialize it, power management, things of that sort. And of course, the driver has buffer and memory management things inside of it. If you take a look at Video for Linux driver, it's just a huge directory. It's like 100 different cameras supported. And what happens is that those top layers on our previous diagram there are all the same, but underneath each camera can have its own file, and you can use that with the top layer. So you can support multiple or many different types of cameras or different types of topologies. Usually these are all done at compile time, so you pick out your cameras that you're going to use, one or two, front-facing, back-facing, compile them in. You want to sort of keep these to a minimum. You don't want to compile them all in because it takes a long time to initialize cameras. And Video for Linux exposes these cameras, has devices in the dev directory, Video 0, Video 1, etc. Some of the kernel resources. Memory is very important, as I said before. You can either allocate buffers in kernel space, or you can do it in user space and have those passed down. When you talk about a camera, you're always thinking that the hardware transfers the image out of the camera into memory. You never hear of anybody pulling the camera for data. That's very old. And also, most modern chips have an MMU associated with the camera hardware. What this means is rather than having one contiguous block of memory for each image, which is very difficult to allocate in a real-time operating system or just any operating system, you can have a scatter-gather memory can be used. So blocks can be placed anywhere in memory, and it can DMA to any of those. Interrupts, of course, are important for the camera. You don't want to pull it. Interrupts, they have different capabilities for interrupting when the frame's finished or starts, things like that. There's the control and the data path for the camera. Control refers to how you're controlling the camera, how those parameters you send down get set. Data is how the image comes out of the camera. I2C has been used for controlling camera register reads and writes for years. I2C is a little bit of a slower interface. 100 kilohertz or 400 kilohertz are the standards, or even a megabit right now. Alternative to that is SPI, which is in use by some camera vendors. Control signals, there's things like reset and standby. You guys are all software people, you don't care about that stuff. So, and then power things. Power management for a camera is very important. You don't want to, number one, have the camera on all the times. It tends to use a lot of power. Number two, you want to turn it off, but you don't want to lose all your data. You want to be able to come up and preview quickly if that comes up, so you want to be able to suspend the camera and put it in a standby state. We talked about the buffering system used for Video for Linux. This is just a drawing of how it works. Depending on the size of the buffers, the number of buffers will be implemented. The CameraHAL and the Video for Linux have a handshake between them. The kernel fills up the buffers, the HAL empties the buffers or chooses the buffers. So it's sort of a back and forth relationship. Buffer filling starts when Video for Linux stream on command is executed, and then stops when the stream off is executed. And it doesn't matter what size of image you're capturing, it uses the same format the whole time. What this very busy table does is sort of outline what happens during preview for the camera. So CameraHAL will send down all of the calls in on the left column there, and these will be converted either into hardware calls or into driver calls. And the last entry on the first table there, imaging is starting with the image enable or preview start. My last slide on the driver. Video for Linux driver has been progressing to the point where there's something called the media controller architecture, and this is fairly new over the last year or two. And this allows the application programmer to control the pipeline, the actual pipelines. So for certain types of camera architecture, you can go in and tell how you want the data flowing through it, through a resizer. Do you want it to have YUV conversion, things like this. This works really well for an open source architecture. Many ISPs and cameras are a closed architecture. It's actually very nice where it's used. One example of that is a TI's OMAP 3 processor. That's an open architecture. You can download documents on the web and use this driver controller for it. The other end of that is proprietary ISPs move their software out of the driver, and this is to avoid open source issues. What they'll do is move the code up into kernel space. Camera hardware overview. This is the lowest level of the stack that we'll be presenting. Basically, from Aptina's point of view, there are two types of cameras. One is just a sensor, what we call a bare or raw sensor. It outputs something called a bare or a Bayer image. It has no or very limited image processing, and it requires image sensor processor, something to do the image processing in hardware, either on the host or on another chip. And it has very simple controls. The other type of sensor is what we call a smart sensor, or a system on a chip sensor. And this outputs a processed image. So this is sort of an all-in-one package. No host ISP is required, and it supports complex, more complicated controls. So bare sensor discussion, there's a bare pattern in the upper left there. This is repeated throughout the array. Used with an internal ISP, so most of the cell phones nowadays from Qualcomm or TI, those chips have internal ISPs, so you'll just attach this sensor to it. For chips that don't have a host ISP, they can use something called a companion chip, which is just a processing, image processing chip. The sensor controls exposure and gains are the two types of controls for a raw sensor. ISP has much higher level controls such as auto white balance or exposure, things of this sort. And here's a block diagram of a simple bare sensor. Down in the lower left-hand corner is the pixel array. It's not drawn to scale. It takes up the whole picture usually. That is read out one line at a time. That goes through what we call an A to D converter, converts it to digital, and then the pixels are read out either an 8-bit, 10-bit, 12-bit, or 14-bit. Most pipelines right now support 10-bit accuracy. They're going to 12-bit in future processes, ISPs. Second type of sensor is called an SoC type sensor. This one will output YUV, RGB, or even JPEG. And it hooks up much simpler. You just hook it up to a host processor with or without an ISP built in. These types of chips were real common in previous years. So earlier days, 4 or 5 years ago, we would sell quite a few of these types of chips. Now that TI, Qualcomm, everyone has a built-in ISP, we don't sell very many of these. Lower profit margin for us, I guess. But here's a block diagram of a SoC type sensor. At the upper left-hand corner is everything that was in the previous sensors located in that block there. In the lower right-hand corner is where most of the image processing takes place. Things like lens shading and correction, changing the color format, things of that sort. And the right-hand control is where the auto functions are, measurement engines, and changes these sorts of things. Also uses electronic rolling shutter for readout. When you're taking a picture and it's moving very fast and you see sort of a tearing, That's a function of the electronic rolling shutter because it's reading one line out at a time, and you're moving faster than that's able to do so. So you get this sort of tearing effect. Global shutter, it takes it all at once. We have sensors that do that that are more common for things like automotive applications. To talk about preview at the camera level, this is my last slide. Really, a preview is just outputting of an image. It's just, but there's several things about preview. You want to keep the power consumption low if possible. You want to keep it the bandwidth low if possible. So three ways of doing this. In previous years, they used something called skipping, which is just skipping every other pixel. So you'll take every odd row and odd column, or skip 3 or 4. Problem with this is that, well, the good thing is it saves power. It's very good for that. The problem with it is you tend to miss things. So if you have fine granularity, you might miss items in your preview. A better way of doing it is something called binning. That's where you combine pixels. So rather than skipping those 2 or 3 or every other one, you combine them into one pixel. And that's good. It's a nice averaging method. It gives you a much brighter pixel. It averages all 3, or actually it combines it, doesn't average. But then you need to process that down to its image also. What newer sensors are doing is they have actual built-in hardware scaler, so they actually have an hardware algorithm that will shrink down the picture.
No more questions for Sol. Thank you guys, appreciate it.